Hello, everyone, at different times all over the world. 8 a.m. in Miami. So it is a pleasure to introduce Professor Elisa Prato from Universita Degli Studi di Firenze. She's one of the pioneers and leaders in the study of these irrational objects, and she will be speaking today about symplectic toric quasifolds. Professor Prato?
Yes, thank you very much. Thank you for this invitation. It's an honor for me to speak in this conference. Hello from Firenze. So I wanted to give today a survey on this topic, symplectic toric quasifolds, without going into too much technical details, but going over some examples. The starting point, so I'm a symplectic geometer, and my initial motivation for studying this topic came from symplectic geometry. So I just want to give a little bit of the background, the basic things that are needed. And the starting point is a lattice in Rn and the corresponding torus. And we suppose that this torus acts on a compact connected symplectic manifold M, and that this action is Hamiltonian. What this means roughly is that there exists a mapping from M to the dual of Rn called the moment or momentum mapping. And under these assumptions, there is a famous theorem that probably everybody has heard of, is the Atiyah-Guillemin-Sternberg theorem dating from 1982, which says that the image of a moment mapping is a convex polytope. It's also a rational polytope. They didn't say that explicitly, but this is obvious from the context. Among this very general situation, we have what are called symplectic toric manifolds, which are the symplectic version of toric varieties. And a symplectic toric manifold, by definition, is a manifold, as described earlier, in which the action of the torus is effective. This means that each element in the torus, except for the identity, moves at least a point in the manifold. And the action is completely integrable, meaning that the dimension of the manifold is twice exactly the dimension of the torus. So the first fact that I would like to mention is part of a result of Delzant, which I will explain fully later. And it says that whenever we have a symplectic toric manifold, the image of the moment map is what is known as a smooth polytope. So I'm going to recall what this means in the context of this terminology and notation. So the smooth, I start with a dimension n, convex polytope, and in the dual of Rn. And we say that it is smooth if it's, first of all, simple, rational, and then it satisfies an additional integrality condition. So let me describe and recall what these properties mean. Starting from simple, the polytope delta is simple if each of its vertices is the intersection of exactly n codimension 1 faces. We call these facets. Some examples. In dimension 2, every convex polytope is simple. And among the regular convex polyhedra, the tetrahedron, the cube, and the dodecahedron are simple. and the octahedron and the icosahedron are not. Rational means that in this context, assume that we have our polytope of dimension n, and every polytope can be written as in the intersection of half spaces in the following way, where D is the number of facets of delta, codimension 1 faces, and the lambdas are real numbers. And the x1, xd are vectors in Rn that are orthogonal to the facets and point inwards. These vectors, I'm going to be using them all the time, and for short, I will be calling them normals for delta. So delta is rational if the normals for the polytope can be chosen in a lattice. And usually when we are in the context of the image of the moment mapping, we consider the group lattice of the torus. So the lattice L such that T is Rn mod L. So intervals, triangles, and rectangles are rational. The first simple examples of polytopes that are not rational are the regular pentagon and the Penrose kite. I will be coming back to the Penrose kite later and discuss this example in more detail. And among the regular convex polyhedra, the tetrahedron, the cube, and the octahedron are rational, but the dodecahedron and the icosahedron are not. The last condition is the integrality condition, and so we start with a simple rational convex polytope, and we want to be able to choose the normals in the decomposition of delta's half spaces, so that for each vertex, the normals that correspond to the n facets that meet at that vertex form a basis of a lattice. So I'm going through a list of simple examples: the interval 0, 1 with lattice Z, the square with lattice Z2, the isosceles right triangle of vertices 0, 0, 1, 0, and 0, 1 with lattice Z2. And among the regular convex polyhedra, the cube with lattice Z3 and the regular tetrahedron when it's suitably placed with respect to this sublattice of Z3 that is generated by the vectors 1, 1, 1. 1, minus 1, minus 1, and minus 1, 1, minus 1, and minus 1, minus 1, 1. Then another example of smooth polytope is the following trapezoid that has vertices 0, 1, n plus 1, 1, 0, 0, and 1, 0. Again, with respect to the lattice Z2, I didn't mention the normal vectors. You have all the obvious choices in the previous examples. Here we have a specific choice, which it's also obvious, but I will describe it in detail later. I will come back to this trapezoid shortly. So Delzant showed several things. As we said earlier, if we start with a symplectic toric manifold, the image is a smooth polytope. But he also showed the reciprocal, meaning that if we have a smooth polytope, there is a construction which is now known under the name of Delzant construction, which enables us to explicitly construct a manifold, the symplectic toric manifold M, starting from delta, having the property that its image, the image of the corresponding moment mapping is delta. So M delta has a torus action with the properties that I described earlier. And what is interesting about this construction is that it's obtained via symplectic reduction, which is the main operation in Hamiltonian geometry. The other interesting aspect of the Delzant theorem is that there is a uniqueness. So up to T equivariant symplectomorphism, this M delta is the only symplectic toric manifold that maps to delta. It's important in order to understand the rest of the talk and the nonrational case to understand how the Delzant construction works. So Delzant wrote the decomposition of delta into half spaces, choosing the normals to be primitive in the lattice. Then he considers the standard Hamiltonian action of the standard torus TD, RD mod ZD on CD by rotations on each component. This is the classical example of Hamiltonian action, and the moment mapping is given by this formula. The moment mapping of an abelian action is unique up to a constant, and Delzant chose this constant to be equal to this lambda 1, lambda d, where the lambdas are the constant that define the half spaces. So that's the first step. The second step consists in taking the normals, and there is a standard procedure for associating, starting from the normals, a subtorus n of the big torus TD. So the idea is to use symplectic reduction. So he takes the moment map of the induced action of n from the big action of TD on CD, and he takes this quotient, the inverse image of 0 mod n. This M delta naturally inherits a Hamiltonian action of the quotient of TD mod n, which is essentially T, Rn mod L. And it's easy to check, it's a computation that the image of phi is delta. So some examples, let me go back to the examples of smooth polytopes that I listed earlier. We start with the unit interval. It corresponds to S2. The square corresponds to S2 mod S2. The isosceles right triangle corresponds to S5 mod S1, which is CP2. And the right trapezoid corresponds to the symplectic toric manifold that is known as Hirzebruch surface, which we denote by Fn. Just to give you a flavor of what is reduced spaces look like, this is the reduced space that one gets from the trapezoid. So it's a quotient of submanifold of C4 mod the action of this subgroup N, which is on the denominator, subtorus. So this is a brief overview of Delzant's theorem. There are several natural questions that arise. The first question that arises is what happens if the polytope does not satisfy the third property, the integrality property. And this was addressed by Lerman and Tolman in the 80s. but it's not difficult to understand what happens if one applies the Delzant construction step by step. One gets orbifolds, orbifold type singularities when one performs the quotient. And Lerman and Tolman have called these spaces symplectic toric orbifolds. Uniqueness fails, but it can be restored if one attaches some combinatorial data to the polytopes. And here it is quite simple. It's enough to attach positive integers to the facets of the polytope. The second question that arises right after the first is what happens if the polytope is not rational? And this is a question that I started working on in the late 90s. The first work was a work that appeared in 1999, which was a research announcement that contains most of the ingredients. So clearly, the old framework was not enough, and it had to be replaced by a new setup. And now I will list the objects. They also appear in the abstract of my talk, and then I will explain what they are and a little bit of the history. So the idea is that I replace the lattice with something more general, which I call which is called quasilattice. Rationality with quasirationality, the torus with the quasitorus, and the symplectic toric manifold with the main object of the talk, which are symplectic toric quasifolds. Let me start with the quasilattice. So at the beginning, I was just working with pen and paper, and it appeared clear to me that lattices were not enough. So I considered just the z-span of, instead of a basis of Rn of a set of finite set of generators of Rn, which we call y1, yd. And clearly, if d equals n, we obtain a lattice again. After a while, I searched a little bit to see if this object was already present in the mathematical literature. And after a while, I ran into them, and I discovered that these objects had been named quasilattices by quasicrystal geometers. And the first time that this term appeared is in 1981 in a paper on quasicrystals by Mackay. Parallelly with the theory of quasicrystals is the theory of non-periodic tilings, and quasilattices are also fundamental in certain non-periodic tilings, namely Penrose tilings. And I want to, I was fascinated when I discovered this, and in fact, in the following years, Penrose tilings were a source of inspiration for my research, and also in collaboration with Fiametta, of course, Fiametta. And we draw inspiration from Penrose tilings, and we try to understand the connection between tilings and the symplectic toric quasifolds. And I will say a little bit about this later. So we have seen that delta is rational if the normals can be chosen in a lattice. So if we replace the lattice with the quasilattice, the rationality gets replaced with quasirationality. So we say that delta is quasirational with respect to a quasilattice Q if its normals can be chosen in Q. One has to be very careful here. Every convex polytope is quasirational, so it's not a restrictive hypothesis. It's just something that helps us keep track of our environment. Everything is going to depend on this quasilattice and on the normals. So we want to know at each stage which quasilattice we are dealing with. Why is every polytope quasi-rational? This will become clearer with the examples that we'll see later. But so suppose we have a polytope like the pentagon, for example, which is not rational. I take the 5 normals to the 5 edges and I generate a quasi-lattice starting with that set of normals. So then the quasi-rationality and quasitorus, I searched and I had not found anything like that in the literature, except for small dimensions. So I named in a very natural way the quotient of Rn mod the quasilattice is quasitorus. If Q is a lattice, then the quasitorus is a torus, of course. And if n equals 1, the object is a well-known object. It's Q is Z plus A. Okay, we can choose Q to be Z plus AZ with A irrational. And this object is present in the literature, for example, in the work of Donato and Iglesias in 1985, and they named it irrational torus in the context of diffeology. But of course, you find this also in the work of Alan Kohn and Alan Weinstein with slightly different names, but it's the same object. So what I did with this new framework, I repeated the Delzant construction step by step, and really formally the same construction, no change. I arrived to the last step and I take the reduced space. The only difference is that the subgroups N now are not tori necessarily, and so the quotients are no longer Hausdorff necessarily. However, what I also noticed is that it's, even if they were kind of wild in this sense, they still retained some of the features of the orbifolds and of the manifolds. That they have these charts, they have this atlas where the charts are formed by open subsets of R2N, model the action of countable groups. So in the case of orbifolds, these groups were finite, but in the general case, they are countable. And I named these objects Symplectic Toric Quasifolds. And there is again the action, induced action of TD mod N. And now the TD mod N is the quasitorus Rn mod Q. So the important remark here is that this construction depends on a choice of quasilattice, as I already mentioned earlier. With respect to delta is quasi-rational. And also on a choice of a set of normals, okay, because all the construction depends on this initial choice of x1, xd. So if you change Q and if you change x1, xd, you will get different quasifolds. Now I want to go over some examples, and the example that is the simplest is the quasisphere. Actually, this example does not come from a non-rational polytope. It comes from the interval 0, 1, which, as we have seen, corresponds to the sphere S2 under the classical Delzant construction. But we changed the quasilattice. We replace Z2 with a quasilattice, and we take two positive integers.
Oh, I don't understand.
No, not integers.
Yeah, okay,
sorry.
gotcha.
Cis, real numbers. I don't know why I wrote integers. Sorry, just a typo. Real numbers. Okay. And so what I do is I take this interval and I consider this quasilattice as z plus tz. And as normals, I consider on the vertex 0 the number t, and on the vertex 1 the number minus s. Usually the classical normals here are 1 at 0 and minus 1 at 1. Okay, so this, I have to erase this. Okay. Okay, so if we perform the generalized Delzant construction, is we get this quotient. So n is acting by these irrational rotations and on an ellipsoid upstairs. This quotient has an atlas which is made of two charts. It's really like the sphere, ordinary sphere, but so we have a south pole and a north pole. The south pole is the point 0 square root of s, so the class around the correspond to this point, and the class of square root of t0 is the north pole. The chart around S is given by the open ball of radius square root of t, with the following group acting by irrational rotations. And U tilde S maps on US, which is the set of points in M delta where W is different from 0. And then we have a homomorphism from the quotient U tilde S mod gamma S to US, which is given with this mapping. It really works very much like in the case of the sphere and the orbispheres, which is the orbifold analog. Similarly, in the North Pole, we have this chart. Really works in the same way. The two, of course, intersect, and there is a transition mapping between these two charts, which is given as follows. So this really gives a flavor of how quasifolds work, and I will give a few more examples. As I said before, a lot of inspiration in the subsequent years came to us from Penrose tilings. We worked with the rhombus tilings, but I'm going to speak about the kite and dart tiling here, which we also worked on. And this is a photo of the, a picture of this tiling. The kite has 3 equal angles, all equal to 2 pi over 5, and the other down here, and this one up here is 4 pi over 5. The long edges are phi times the short edges, where phi is the golden ratio, 1 plus square root of 5 over 2. And as quasilattice, we consider the following vectors in R2, which are portrayed by this star, phi at the 5th root of unity. And the kite is quasi-rational with respect to this quasilattice. And the normals are x1 equals minus y1, this is y1, so it has to point inwards, so we change the sign. X2 is y2. X3 is minus y3, again, it has to point inwards, and X4 is y4. So if we apply the generalized Delzant construction, we get this quotient. And what we showed is that this is not a global quotient of a manifold modulo the action of a countable group, which makes this example quite interesting. Yes, let me go back to the trapezoid. The kite was joint work with Fiametta, and this discussion on Hirzebruch surfaces is joint work also with Zaffran. And let me go back to the trapezoid that we considered earlier. I will show the normals here. They are given by, these are the primitive normals that are needed for the classical Delzant construction. They're these vectors, 1, 0, 1, minus 1, n, 0, minus 1, 0, 1. And the natural question is, what happens if we replace n with any positive real number a? And one gets this trapezoid where this vertex now has coordinates a plus 1, 1. And if a is irrational, this trapezoid is not rational with respect to z2. And we want to keep, for reasons that we will be clear as we go on, we want to keep this lattice fixed. So what we do is we mimic, we mimic the normals. We took exactly the same normals as the standard Delzant case, where instead of n here we have a, the others are the same. Notice that if a is irrational, this vector is not going to hit z2. They generate a quasilattice that in general contains z2, which is given by z cross z plus az. And if we apply the generalized Delzant construction with respect to these choices, so we have the trapezoid, we have the quasilattice, we have the normals that are fixed, we get the following toric quasifold. If we go back, this is exactly this, and look at what we had written earlier. I'm not going to do this, but it's exactly the same as before, but with an a instead of n. In fact, if a equals n, qa is z2, and fa equals the classical Hirzebruch surface Fn with the action of the standard torus. So the Fa can be thought of as a one-parameter family of spaces that contains the Hirzebruch surfaces as special cases when a is an integer. This will be current examples. Fiametta is going to talk about this again in a different context on Wednesday. Now I just wanted to give a little bit of history of toric quasifolds in general. In joint work with Fiametta, she will be discussing this in the second talk. We considered the complex setup, so we constructed the general toric variety as a complex quotient, and we obtained the complex toric quasifold on dimension n with the holomorphic action of a quasitorus, which is the complexified of the, yes. And there is a diffeomorphism between the x delta, this quotient and the M delta that I described earlier. And the symplectic form is compatible with the complex structure. So we have a Kähler structure on M delta, X delta. The third natural question is, so the first was what happens if the polytope doesn't satisfy the integrality condition. The second was what happens if the polytope is not rational. The third question Fiametta addressed was what happens if delta is a general polytope, meaning that it is not even simple. So we already mentioned two important examples are the regular octahedron, which is rational, but it's not simple, and the regular icosahedron, which is neither rational nor simple. So Fiametta has extended both constructions to this setting, both the complex and the symplectic construction, and the spaces that she obtained are even more singular, of course, but she found out that they are stratified by symplectic and complex quasifolds, and she will talk about this in more detail later. I just wanted to remark that these results are relevant also in the rational case, most of the results. And they are new also, they were new also in the rational case. So we, as a fun project, we applied her general construction to the, we computed the toric spaces corresponding to the 5 regular convex polyhedra. Also, these are the dates that the papers appeared, but the original archive versions were a few years precedent. Okay, now I want to discuss some more recent, I'm keeping an eye on the clock here. Time is going fast, but I will briefly go over some more recent results. This is also joined with Fiametta from last year. Symplectic reduction is the main operation in Hamiltonian theory of Hamiltonian actions, and we were interested in understanding whether this operation carried through for symplectic toric quasifolds, and so we found out that if we start with a polytope that is quasi-rational and a set of normal vectors, and we consider the corresponding symplectic toric quasifolds, then we can reduce with respect to the action of any subgroup of the form K, mod K intersect Q, where K is a subspace of Rn. And so I want to go a little fast here because I see that I'm running short of time, but so we have a symplectic reduction theorem, and the result is a symplectic toric quasifolds, and this allows also to reduce the symplectic toric manifolds with respect to general Lie subgroups, not necessarily closed. And of course, the result is a quasifold in general. And so also the other remark is the symplectic toric quasifolds are closed in the symplectic reduction, unlike the smooth and orbifold case. So the thing that I wanted to spend a little more time on is the symplectic cut operation. This is an operation that is due to Eugene Lerman. So we take compact connected symplectic manifolds with the Hamiltonian action of a torus. We take the image of the moment mapping, which is a convex polytope, which we have represented with this triangle. Then we consider a hyperplane corresponding to an element in the lattice and a certain real number epsilon. For suitable L and epsilon, this hyperplane will cut the polytope. And this cut will produce two convex polytopes. which are intersection of the original polytopes with the two half spaces. And Eugene Lerman showed that this cut at the level of polytopes has a correspondence at the level of manifolds. So under regularity assumption on the component, on the y component of the moment map, he constructed two compact symplectic orbifolds, each with an action of t, such that the corresponding moment mapping images are given by the two cuts that we have seen in the previous slide. Okay, so each of the little smaller polytopes actually corresponds to, is the image of a different moment map and manifolds, symplectic manifolds. These spaces are obtained by symplectic reduction. So going back to my joint work with Fiametta and Zaffran, an important, interesting, let's say, remark is that the Hirzebruch trapezoid can be obtained by cutting the infinite strip 0 plus infinity times 0, 1 with this line x equals ny plus 1. And so even if the strip is not really a polytope, but it still corresponds to a symplectic manifold, toric manifold. It's non-compact, but it's a simple variation of the Delzant theorem that allows this as a symplectic, also toric manifold. And one gets C times S2. So one can, it turns out that Fn, the classical Hirzebruch surface, is the symplectic cut space M plus, where we choose y to be minus 1n and epsilon equals to minus 1. With Fiametta, we decided to generalize the symplectic cut operation. Our motivation came actually from tilings originally, and I will try to say a little bit of this in a few minutes. So under certain assumptions, we were able to generalize Lerman's result, but still in the context of the toric quasifolds, Lerman result did not require the manifold to be toric, and it was more general in that respect. Here it's more general in the respect that we are in a non-rational setting. So basically we were able to do the same thing, but so we did not really require, as Lerman did, that epsilon was a regular value. This is perhaps a little technical. What is more relevant here is that M plus and M minus are the quasifolds that correspond to delta plus and delta minus under the Delzant construction. So this also is a classical thing that holds in the smooth case that carries on in the non-rational case. So why Penrose? Because if we cut the Penrose kite in two as follows, we get a decomposition into what are called golden triangles. And this is a classical tool that is used in Penrose tilings, for example, to pass from a kite and dart tiling to a Penrose tiling. So the idea is briefly described by this picture. The kites are divided in two and recomposed in order to be in these two possible ways to form Penrose rhombuses. So when we cut the quasifold corresponding to the kite, this is what we get with our generalized cut procedure. Now I want to go back to the generalized Hirzebruch surface. And of course, the natural question is here, can we obtain the generalized Hirzebruch surface as a cut using the generalized cut operation? The starting point is would still be C mod S2 if we attempted to use the Lerman construction, but we cannot use the standard Lerman construction because the Y that defines the line that supports the line will not belong in Gen O to Z2. So the question here that we need to address is how to cut a smooth manifold in an arbitrary direction. So more generally, we address the idea of cutting a quasifold with an arbitrary direction that was not belonging to the initial quasilattice or in the initial lattice, if we think of the previous example. So the idea is to consider the quasilattice that is generated by Q together with Z times Y, the new vector, supporting vector. So if we apply the generalized Delzant procedure relatively to this new quasilattice, we get a new toric quasifold, which is a quotient of the previous one, modulo the discrete group given by the quotient of the two quasilattices, the countable group. So the idea now is that we can apply the cutting procedure to the new quasifold. And this is what one does also to cut manifolds and orbifolds in arbitrary directions. So the idea for the Hirzebruch generalization is that we add the vector -1a to Z2. So we again get this quasilattice, and we consider the manifold corresponding to the strip, but with this new quasilattice, this normal vectors, and the new quasifold, the new manifold, it's no longer the new space that we get is this quasifold, where gamma A is a group of irrational rotations acting on S2 as rotations around the Z axis. So basically we apply the generalized cutting procedure, and we get that the FA, the generalized Hirzebruch surface, is the cut M plus, exactly like in the smooth case. So this is a nice way of visualizing the one parameter family of Hirzebruch surfaces. If we look at the level of the polytope, we see this trapezoid varying as we move this, as A varies and this line moves. Okay, so I have 1 minute. I have finished. I just wanted to go over quickly the bibliography, all the works that have been cited. This was the first work where everything started in the last century, and then this was the full-length paper, then the paper with Fiametta on the complex case. This is the paper of Fiametta on the non-simple case. Then our papers on tilings, one on the Penrose rhombus tilings, one on the Penrose kite. Fiammetta's paper on the Betti numbers, which we will address later. And then the general complex non-simple case. Amman tilings, which are a 3D version of Penrose tilings, rhombus tilings. And then the regular convex polyhedra, first the dodecahedron and then all the others. The cuts, the reduction, the Hirzebruch surfaces, and then very recently a work connecting quasifolds with the theology that is joined with Symplectic Iglesias. Other recent works, besides the one which will be discussed, of course, Fiamma will talk about her work we've done on foliations, but besides from this, I wanted to point the attention to other works on non-rational polytopes, besides the one that I already discussed in the conference. And there is a string of works of Jamar and Ratio and Hoffman on non-rational polytopes from the symplectic viewpoint. And the last work in particular is a classification theorem of Hoffman. He introduces toric symplectic stacks and he classifies them using the polytopes, the simple non-rational polytopes with additional data, which of course corresponds to our quasilattice and choices of normal vectors. So this is it. This is the end of the talk. Thank you very much.
Thank you very much. Thank you very much. We can react like this also.
Yes.
Thank you very much for such a nice talk. Is there any questions from the audience?
Yeah, I had a question about the symplectic cuts.
Yes.
So this, you have a polytope and you draw a line across it. And this ends up, you can think of this as bending the polytope up, making it a convex tent over the polytope. Can you do this more generally for any convexification? You know, like for instance, like take a point in the middle of the polytope and lift it up and look at the convex, the upper hall of that. Do you get it? Because in algebraic geometry and also in this area, it's very natural to take such to do such a construction. It's a degeneration of the original object.
Yes. Well, these are cuts that you slice and you cut in
I see
two.
that.
Yes.
But,
I don't know. It's quite likely, but I haven't thought about it.
Because you get the same object. You get an object which is a union of these toric varieties for these different pieces, and each of them has a moment map which maps onto the piece you're looking at, and it's actually quite natural.
Yes. Okay. So yeah, they must be definitely related. Yes.
Any other questions? Well, if not, let's thank Professor Prato again.
Yes, you're welcome. Thank you for this opportunity.